We have two more talks, one by Justin Drake and one by Elaine Shih. I'm very happy to call Justin to the stage. He's a researcher at the Ethereum Foundation, and he will tell us more about encrypted mempools.
Okay, encrypted mempools. To me, a very important topic because it kind of addresses two of the big problems in the space that we have right now. One is front running, and the other one is censorship. So I was asked to talk about, I guess, both the intersection of crypto and economics, and I traditionally lean on the crypto side of things. So I kind of picked a case study which had a bit more economics in it, and I think encrypted mempools is a good example. So we have the encryption side of things with the crypto, and on the economics we have these auctions, these transactions auctions with mempools. And like one of the things that I kind of want to highlight here is that in the 2010s we've been building blockchains with very simple cryptography, with hash functions and signatures, and I think there's going to be a shift in this decade where we're going to be using much more powerful tools. And so, I think sophistication will grow, and if you want to be doing economics in the blockchain space, you need to be comfortable with these cryptographic tools. At the very least, you need to understand the APIs. What do they do, and what power do they give you? I kind of think of Ethereum as this machine, that produces real-world cryptography. So that also makes it exciting. Ethereum really is at the forefront in terms of real-world cryptography. So, I'll explain what is an encrypted mempool, like just the basic framework. Then I'll explain, why it's good to have encrypted mempools, and then finally, get our hands dirty with some of the details around how we handle, metadata, which is one of the main technical complications. So the simple framework of encrypted mempools is that as a user, when you want to broadcast a transaction, you broadcast it encrypted to the mempool, and somehow this encrypted transaction gets committed. So, for example, it gets included on chain, and only after there's this credible commitment which is made that it will be included and will be processed on the blockchain do you decrypt and execute. And from a user experience standpoint, like these three last steps, commit, decrypt, execute, can all happen on-chain in a single slot. So it doesn't have to be a departure from the current user experience. There doesn't have to be any additional latency, is what I mean. Now, one of the things that's important is basically for the decryption step to not rely on the user. You don't want to have a commit-reveal scheme where you're depending on the user to reveal the ciphertext or decryption key or anything like that. Really, you want to have this forced or guaranteed decryption. And it turns out there's various ways to have this guaranteed decryption that rely on different assumptions and different levels of sophistication. So I'll just go through them real quick. So the first one is like the most simple form of encryption you can think of, which is kind of this in-flight end-to-end encryption between you and a trusted third party. So this is what Flashbot Protect is. It's kind of this encrypted mempool to a trusted third party. So you're sending your transaction to your third party, and you're hoping that this third party doesn't leak. You're trusting it that it doesn't leak your transaction before including it on chain. You could also use trusted hardware and enclaves, and Flashbot is working on this with Suave. You could also have threshold decryption, where basically you have a committee which is going to be doing the decryption. And you have projects like Arbitrum and Shutter that are going in this direction. This is one of the more popular approaches. You have this piece of cryptography called delay encryption, or you could say delay decryption, whereby your ciphertext automatically decrypts after time passes. And this is closely related to a primitive called VDFs, verifiable delay functions. And then you kind of have the mother of all kind of guaranteed decryption schemes called witness encryption. And basically the idea of witness encryption is that you can use any witness as your trigger to decrypt a ciphertext. And one of the things you can do, for example, is combine the power of threshold and delay. So for example, one of the failure modes of the threshold decryption is that what if the committee goes offline or you can't reach the threshold, then maybe you could have a fallback whereby a few seconds later it gets decrypted if the fast path of the threshold doesn't go through. So in terms of readiness, the first three are ready for prime time in production. Delay encryption is coming soon. Like one of the hard things about the delay encryption is that you need ASICs. And actually the Ethereum Foundation has started the process of building an ASIC, and in a few weeks we'll have the first test samples. It's kind of this VDF ASIC, which also works for time lock puzzles and delay encryption. And witness encryption is mostly at this point a theoretical thing. It's just extremely, extremely hard, but it's kind of interesting to put on the slides from a theoretical standpoint. Now, one of the things that I kind of want to highlight is that for every single flavor here of decryption, you can have a homomorphism. The kind of a homomorphism is kind of this idea that you can operate on the ciphertext. So let's say that you have the encryption of two transactions, M1 and M2, and you kind of want to apply some sort of function on M1 and M2, given only the encryptions, not the plain text. And that's basically a piece of magic called homomorphisms. And you may have heard of fully homomorphic encryption. And so really the M's here in our use case are going to be transactions, and the F is going to be build a block, for example. So you have all these encrypted transactions, and your goal is to build a block given these encrypted transactions in the mempool. And in terms of where we're at for the homomorphism, in-flight and enclave, it's kind of trivial, because when you have a trusted third party or you have trusted hardware, like these have access to the plain text, and so they can apply all sorts of functions F that they want. There's a lot of progress with basically FHE, at least for simple functions. So I think this will be one of the frontiers here. This threshold column with FHE hopefully coming soon. Okay, so why do we want encrypted mempools? We know what they are. They're just the same as we have today, but where the transactions are encrypted. And as I alluded to, there's two big reasons. Reason number one is to remove front running. So you don't want to be the salad and the cheese in that sandwich, basically. So we want to try and remove front running. And the intuition here is that if no one knows that you're cheese, then no one can put the bread around you. So if you can't see the content of your transaction, it makes it extremely difficult for searchers to front run you, because in the ideal case, the encrypted mempool just looks like perfect white noise, and so there's no information to be extracted, and so you can't make informed decisions around front running. At least not from gleaning from the mempool. And then the other kind of related problem with front running is this idea of sophistication, right? Like in order to be the one that detects cheese and applies the bread, you need an army of PhDs, maybe at Citadel or whatever, and you need powerful computers, and so that's bad for centralization. And so we want to kind of reduce the surface opportunity for being sophisticated by removing the sandwiches. So basically, there's two, broadly speaking, there's kind of three types of transactions that I conceptualize. There's some very simple transfers, like NFT transfers or ERC20 transfers, where there isn't necessarily much front running or MEV to be extracted. And then there's these two classes of the sophisticated MEV. There's the arbitrage and the front running. And by removing the front running, we're significantly removing the need for sophistication in block building. The other problem is censorship, and one of the one of the ways to think about how encryption helps with censorship is that when you're building a block and you want to censor some types of transactions, if you can't see the contents of encrypted transactions, then you have to censor all the encrypted transactions. It's like an all or nothing thing. And so if we're in the position where the vast majority of transactions are encrypted, if like by default wallets will encrypt your transactions, then let's say 95% of all the transactions and all the priority fees will have to be not included in blocks, and so you'll have a huge handicap as a builder. So basically, if you want to be a censoring builder in the context of an encrypted mempool, you have to give up a huge chunk of your profits, and so you won't be a competitive builder, and so you won't be able to be successful as a censor. Does this make sense in terms of like the broad framework and the motivation? Any questions so far? Okay,
I have a question about
yeah.
censorship. Like, you're actually a powerful censor, and people who encrypt can't just demand that they give you a decryption, or you even ask that they prove with $0 that their encrypted transaction doesn't violate.
Right. Yeah. So that is right. So the question is like, is it possible that, for example, some governments say it's okay for you to use the encrypted mempool, but you must prove in zero knowledge that you're not, touching, OFAC addresses, for example. And yes, that is something that can be done. And basically that you fall back to the status quo, where it's almost as if you don't have encryption. And so here, basically, from the censorship standpoint, is not a like 100% bulletproof solution. It's more of a mitigation, and we have other ideas that complement encrypted mempool. So we have this idea of inclusion lists and MEV burn that also help with censorship. So this is not the full story, but in my opinion, it's at least half of the story. So it's like maybe the lowest hanging fruit in terms of having a huge impact and being possible to do, for example, within the rollups. So you could have each rollup could have its own encrypted mempool, and this is something that, for example, that Arbitrum is exploring. And my guess is that in, let's say, 3 to 5 years, every major rollup will have their own encrypted mempool, and maybe one day we can envision having Ethereum Layer 1 itself having an encrypted mempool, but maybe less of a priority than the rollups. Okay, so here is where kind of the technical stuff comes in. So the problem is that you can't just encrypt a transaction and hope for the best. You actually need to be very, very careful about what exactly is a transaction, and try to not first of all make sure that these things are valid objects that you're working with, but also not to leak from the metadata. So when you have a transaction, there's actually many things at play here. So first of all, there's maybe an IP address associated with whoever's broadcasting the transaction. There's the size of the transaction. How many bytes is the transaction? Who is the sender? What is the tip? What is the gas price set? What is the gas limit? What is the nonce? What is the signature? And there's what is the time at which the transaction was broadcast? And you basically need to handle them one by one in order to have a perfectly encrypted mempool with like zero leakage of information. So my claim is that it is possible to work through all of these one by one, but it requires a bit of work. And I kind of want to give you a bit of intuition in terms of the tools that we can use to handle these pieces of that metadata one by one. So IP address, when you're broadcasting your transaction, that's fairly easy. Just use a private broadcast network, something like Tor. I mean, it may be easier said than done, but at least it can be done. Can be done in theory. Now, one of the things that you want to do basically is check that the encrypted transaction is a valid transaction, and in particular that it has a valid signature. And so what we're going to do here is we're going to use snarks. And a snark basically has like three important things at play. It has the public input, the private witness, and the statement that you're proving. And so the public input, which is something that visible to the whole public, that's going to be your ciphertext, your encrypted transaction. And then as a user who's kind of preparing this encrypted ciphertext, you have access to the plaintext, and really what you want to prove is that the ciphertext is a valid transaction, and that the ciphertext corresponds to the plaintext. And so part of the statement is just proving that the ciphertext is valid, but you also want to prove that the signature is valid. But then what do you need to do to prove that a signature is valid? You need to get the pub key associated with an account, right? Because you verify signatures against a pub key. And so you need to go fetch this pub key along with a Merkle proof corresponding to a state root. You provide that as the whole thing as a witness. You verify all of this within the snark. You verify both the Merkle path and the signature within the snark. So there's a little bit of work to be done here. And so basically what I'm saying here is that in addition to having the encrypted transaction, there needs to be an associated snark that proves that this encrypted object is a valid transaction. So you want to prove that the signature is valid. Now you could do a similar thing for the gas payments. You want for the transaction to be valid, you want to make sure that the sender balance has enough, ETH basically, to be able to pay for the fees. And so you need to do the same thing here. You need to go fetch the balance associated with the current state root, verify the Merkle path, and then verify that the balance is sufficient to pay the 21,000 gas or whatever it is. And you could do the same thing with the nonce. So the nonce is meant to be this strictly incrementing number that increments by 1 every time you make a transaction. And basically you want to prove that the nonce of your encrypted transaction is indeed the old nonce plus 1. But this is actually not sufficient. So this is where you kind of need to be a little bit more sophisticated. And the reason here is that this is actually vulnerable to a denial of service attack. So one of the reasons why we have nonces is basically so that you can't just spam the mempool with all sorts of different transactions with the same nonce. Like the nodes will only look at one transaction with that nonce. And so really what we want to be doing here to preserve this anti-DOSing properties, we want to have a replay tag. Basically, we want to have a way to uniquely tag transactions, and in such a way that if as an address owner, I can't just spam 1 million transactions for this one address. And one way to do it is just to make the replay tag be the hash of the nonce and the private key. So basically, because the nonce is fixed and the private key is fixed, the replay tag is going to be fixed. And so even if you prepare two completely different transactions, they're going to have the same replay tag, and so you won't be able to DDoS. But maybe this is still not a perfect solution, and the reason is that what if the gas price has moved against you and you want to rebroadcast your transaction with a higher gas price? Then basically we need to add a little bit of flexibility to update this replay tag. And so maybe we should add the slot as part of this. So basically you can only broadcast one transaction per address per slot. Okay, now let's look. Sorry, what? Yes, but the thing is that there's only one valid nonce at any given point in time. So So part of the, so you see there's this new nonce valid. New nonce valid means that it's the old nonce plus 1, and so you can't just pick 20 or 100. It needs to be the old nonce plus 1 precisely. Okay, so another problem is around leaking the size of your transaction. So generally speaking, if you encrypt a plain text of size n, the ciphertext will also have size n. So it leaks the size of the transaction, and maybe that's enough information for people to front run or censor you. And so one of the ideas to deal with the size is to basically pad transactions to the nearest power of 2. So if one transaction is, let's say, 5 bytes, you can pad it to 8 bytes. 7 bytes also pad to closest power of 2. And then when you build your block, you just concatenate these padded ciphertext. But there's a couple of problems with this solution. The first one is that you have imperfect packing. So all these like white little squares, they're just basically encrypted zeros. And you have to pay for them. You have to pay the data availability to put them on chain, which is suboptimal. And the other thing is that you have imperfect privacy. And the reason is that there's multiple valid powers of 2, and so for example, the first 2 transactions here are distinguishable from the third one because they have different lengths. And so this brings us to idea number 2, which is to use homomorphisms, the magic. So one of the things that you can do basically is you pad your transaction to the maximum transaction size. So let's say the maximum transaction size here is going to be 16 bytes. And then you use as your function f in the homomorphism the pack efficiently function. So basically you'll be able to pack these transactions without any padding. Just remove all the padding. And so here we have a solution where the encrypted transactions all look exactly the same. They're indistinguishable. They all have the maximum transaction size. And you have this optimal packing in play. So you're paying the minimum fee that you could for your transaction. It's red. It looks exactly byte for byte the same. Yeah. Sorry. So what's shown here is the plain text. Not the encryption just looks like white noise. It looks like gray. It's all gray if you're looking at the encryptions. But if you're looking at the plain text, it looks colorful, and this is what the function f does. It's the packing function. Yeah.
How would you know that the encrypted transactions would all fit in this maximum size? They all fit the same.
Right, so but that's kind of the definition of the maximum size. So in the case of Ethereum today, we have a gas limit of 30 million gas, and so you could that corresponds to a maximum transaction size. I don't know, 100 kilobytes, let's say. And so every transaction could just pad to 100 kilobytes, and then you just feed them through. But it doesn't have to be dictated by the gas limit. You could have maybe a more reasonable, you could say 99.99% of transactions are less than 10 kilobytes, and so we can just pad to 10 kilobytes and call it a day.
How would you know how many?
Oh, how many? So what you do is that you just pack as many as you can to form a block. So if there's let's say 1 million transactions and there's not enough space in the block, your homomorphism will do just pick the best transactions and put them in. And actually this brings me to the next slide, which is that you kind of want to order the transactions in some way or another. So you might want to prioritize by tip, for example. So in this case here, like the ordering of transaction 2 and transaction 3 would be flipped, and you have a different packing at play. And this is important in the context where you're going to have more transactions that you can fit in a single block. Yeah. Okay. Yeah. And one of the things you can do is that you can instead of working with tips, you can also work with access lists. And so this is a way, for example, to combine bundles, right? You can have your homomorphism kind of pick the best ordering of bundles where each bundle is kind of disjoint from each other from an access list standpoint. And then there's this idea which I realized this morning, which is pretty cool, which is that it turns out that you can also deal with the leakage of the mere existence of the transaction. So you'd think that when someone makes a transaction at a given point in time, the fact that this ciphertext can be observed is in and of itself a leakage which is fundamental and it cannot be hidden. But actually, maybe it can be hidden. And the idea here is that what if we allowed every single validator, so right now there's about 500,000 validators, the ability to make a dummy transaction, one dummy transaction per slot. And so they'd be able to insert these dummy transactions in the mempool and do it in such a way that they would add this white noise so that at any given point in time, the mempool is perfectly full. So it's a bit like noise cancelling headphones, where you add the negative, of the sound, and then you kind of get this white noise. It would be the same thing here. So whenever there's a spike of transactions, fewer dummy transactions come in. If there's a lull in transactions, these validators kind of fill in the mempool with dummy transactions, and then your fully homomorphic encryption is just going to remove the dummy transactions because it can detect that it was the one transaction that was made by a validator, which has a special dummy flag that was used purely for the purposes of hiding the timestamp. That's it. I believe that we can build these mempools that leak zero information and thereby solve censorship and front running. Thank you.
Thank you, Justin. Since we're a little late on schedule and we had some engaging questions during the talk, maybe we can keep more questions for the afternoon session, which are AMAs with the speakers of the morning. And we will now move on to Elaine Shi, Associate Professor at Carnegie Mellon University, for her talk. We have the slides here.
Yeah, I'm very excited to be here. I actually had to teach a class in Tim's office in the morning, so I missed most of the exciting talks in the morning. But I look forward to the exciting sessions in the afternoon. I'm going to talk about decentralized mechanism design, and particularly in this talk, I'll focus on transaction fee mechanism design. And the talk is based on two works joined with my student Hao Chang, and then the second paper is joined with my students Hao Chang and Ke Wu. Okay, so you've heard a lot about the transaction fee mechanism design problem. The block size is limited, and we want to pick among these bits which bits to confirm. Okay, and every time a block is mined, essentially you have to run this auction. So as we know, Bitcoin just deploys a very simple first price auction, meaning you pick the k highest bits, where k is the block size, and everyone pays their own bit, and all the payment goes to the miner. And as we know from classical mechanism design, this is not an awesome auction because users are incentivized to bid untruthfully. Like for instance, my best strategy may be to bid the bare minimum that allows me to get in, but I want to pay the bare minimum. Okay, so by the way, if you have any questions, just feel free to interrupt me in the middle of the talk. And so why don't we use all the wisdom we have gained from classical mechanism design? The problem is that classical mechanisms fail in this decentralized environment. Let's take second price auction as an example. So this is like the poster child of classical mechanism design, right? And in this case, let's imagine we want to run second price auction, and the block size is 4 in this case. So second price auction says they should pay the 5th price. And we know in this case, it would be incentive compatible for the users. Everyone would be incentivized to bid truthfully. But the problem here is that even the auctioneer, namely the miner, can be a strategic player. So imagine the miner injects a bid 5. So now everyone will end up paying 5 and the miner can earn more. So that's why second price auction just doesn't work in the decentralized environment, because we also have to worry about incentivizing the auctioneer to behave honestly. Okay. So that's why we need to rethink mechanism design in the decentralized environment. And I think this is a very exciting problem area. And the key question we want to ask is, okay, what is the dream transaction fee mechanism? So there's a line of works, even before our work, that looked at this problem, and they suggested various mechanisms. So it looks like all of these works share something in common, like they agree on the set of desiderata. So first, we want user incentive compatibility, the classical notion we always had, meaning we want to make sure the user's best strategy is to behave honestly, meaning bid truthfully. But in the decentralized environment, we want a couple more properties. We want miner incentive compatibility, meaning we want to incentivize the miner to also behave honestly, implement the honest mechanism. We want resilience against miner user collusion, right? So lots of you mentioned, like there are middleman platforms like Flashbot that facilitate miner user collusion. You can also use bribery contracts. And so we call the CSCP, C side contract proofness, where C is the maximum number of users the miner can be colluding with. So it's parameterized by C. And we want to make sure even when the miner is colluding with MOC users, the coalition's best strategy is just still to behave honestly. Okay, so these two properties are new and they arise in the decentralized environment. Okay, so in this elegant work by Tim Roughgarden, he asked an important question: can we have a dream transaction fee mechanism? So because if you look at the line of work on transaction fee mechanism design, all of the mechanisms known to date, they fail to satisfy all 3 properties at the same time. So you may wonder, okay, is this just a coincidence or is there some fundamental mathematical barrier? And what's interesting is like what comes closest to satisfying all 3 properties is actually Ethereum's 1559, which was rolled out in August last year. And I'm not going to describe the mechanism in full, like for the purpose of this talk, it's not too important. But at a high level, the mechanism has 2 modes of operation. When it's congested, meaning there are more eligible bids than the block size available, it acts like a first price auction. And we know in this regime, this is not an awesome auction, right? So when things are not congested, when there's ample block space, then the number of eligible bids, it acts like a posted price auction, meaning there's some fixed posted price, and if you bid at least this posted price, you'll get confirmed, and all the confirmed bids, they just pay the posted price, and importantly, all the payment is burnt. The miner doesn't get any transaction fee. The miner is getting a fixed block reward still, and this is why miners are incentivized to participate, but this fixed block reward is a constant as far as the game theoretic analysis is concerned, so we just ignore this block reward in the modeling. So Tim, yes, question.
So my understanding that we want to report truthfully is because we want to maximize profits for the validator. Maybe there is some other reason that I don't know, but what's the sort of the equation behind it? But if we start learning payments and we do it in 1559,
Yes.
what's the value of truthful reporting?
That's an excellent question. So I guess, so because this is a new space and we don't even understand feasibility yet, so our approach is we first start understanding feasibility. We want to understand what is the solution space of mechanisms that do satisfy these incentive compatible properties. And once we understand the solution space, you can ask, okay, in the solution space, what is the profit maximizing auction? What is the social welfare auction? So let's first start with feasibility. Okay. So great question. And the Sperm rule is actually new, and I'll revisit it later. But the point is, like, Tim actually showed that, this posted price auction, when the block size is infinite, which means the same as when there's no congestion. So under infinite block size, this is a dream auction. It satisfies all 3 properties at the same time. And that's great. But in practice, I guess, after 1559 was rolled out, I think I guess Tim told me about like 10% of the blocks are double in size, meaning like there's congestion 10% of the time. Like for instance, when there's an NFT drop, and when the price goes up, and in these cases there will be demand spike. So it is still open, and if the block size is finite, can we have a dream transaction fee mechanism? So this is a question we want to answer. Basically what I want to talk about for the rest of the talk is, first I will tell you that unfortunately there is indeed a mathematical impossibility. It's not a coincidence that all these attempts before, they failed to satisfy all three properties. It's impossible. And then, given this impossibility, like I want to ask, if we are allowed to use cryptography, like Drake talked about using crypto, like if we are able to throw in cryptography, can this help overcome these impossibility results? And finally, along the way, I'm going to kind of, whenever appropriate, I'll mention some of these new elements, like the Bern rule. How does it help in transaction fee mechanism design? Does it help to increase the expressive power of transaction fee mechanism design? Okay, so this is the plan. And basically, I'll start with impossibility proof. I'm not going to give the full proof. I'll go over some key steps to give you some intuition. And then I'll talk about crypto meets decentralized mechanism design, and I'll end with some open questions. Okay, so before I prove this impossibility, I actually want to go over a strawman example. I mean, the strawman example is not a proof, of course. It's not an impossibility proof, but it helps to give some intuition. So as I said, in the infinite block size regime, 1559 is dream. Okay, so let's do a thought experiment. So now suppose block size is finite, and we want to tweak this dream mechanism to work for finite block space. And how do we tweak it? I mean, the issue is like if there are many, many bits that are eligible, meaning they're bidding at least the posted price, but the block size is limited, we have to pick among these eligible bids. So how do we pick? The most naive idea is we pick at random. So among all the eligible bids, we pick a random subset of size k, where k is the block size. So the question I want to ask you is like, is this simple modification, is this strawman scheme an awesome auction? Is this an awesome auction? I mean, of course, the answer is no, right? Because I've already told you there's an impossibility. But it helps to understand why this particular auction isn't awesome. Does anyone see why? Yes, in the back. You're getting to the point, but it's not precise. So the problem is not with miner incentive compatibility, because all the payment is burnt and the miner just always gets nothing. But you are getting to the right point in the sense that the problem is like the miner doesn't have to enforce the honest rule. Like it doesn't have to pick the coins honestly. In particular, imagine this scenario. The posted price is 5. And here many people are bidding 10. They all want to get in, but the block size is only 2. We can only accommodate 2 of them. So now, let's say Tim is miner's friend. And the miner will tell Tim, if I were to run the honest mechanism, the chance of you getting included is 2/6. It's like 1/3. But now I can pick my coins such that you are definitely included, in which case you'll get positive utility, and the coalition will gain as a whole, right? So the point here is that the reason why finite block size is hard is because the miner can help the friend, because there are many people competing to get in, and the miner can give the friend the advantage, like ensure a spot for the friend. And this will arise in the impossibility proof, and it will arise again as I talk about how crypto can help, like because we want to kind of make sure the miner cannot arbitrarily choose which set to include. Okay. So this is the statement we want to prove. Assuming the block size is assuming block size is finite, then no non-trivial transaction fee mechanism can satisfy both UIC and one SCP. So one thing you might have noticed is that in the theorem statement, I didn't even mention MIC, because I don't need MIC to rule it out. I only need 2 properties to rule it out, which makes the impossibility stronger. And as far as SCP is concerned, I only need 1 SCP, meaning it's impossible even when the miner is allowed to collude with only 1 user. And that makes impossibility stronger as well. Okay, so in order to prove this theorem, the proof has 2 main steps. And the key intermediate stepping stone is to prove this key lemma, which says if you want UIC and 1 SCP, then miner has to make no revenue, meaning everything has to be burnt. And this key lemma holds no matter whether the block size is finite or infinite. And this is quite interesting because it reminds us of 1559, right? Because we said 1559 is dream under infinite block size. And it so happens that 1559 burns everything. And it turns out this is inevitable if you want to have a dream mechanism, even in the infinite block size space because of this lemma. So that's quite interesting. And once we prove this lemma, we can then throw in the finite block size assumption, which leads to our final theorem. So today, what I will focus on, so I'm actually not going to talk too much about how to prove this lemma. I will focus on the second step of the proof. But just for those of you who might be curious, at a very, very high level to prove this key lemma, what's the idea? So we want to characterize the solution space of UIC. And this is characterized by a classical lemma called the Meyerson lemma, because UIC is a classical property. So once we can characterize the solution space of UIC, we can then show that the requirements imposed by Meyerson actually contradicts with the requirements imposed by 1 SCP. And then we can rule it out. Okay, so I will not go into details here, but this is how you would prove it if you wanted to. But let's assume this lemma is true. And now let's prove the theorem. And at this point, we want to use the fact that the block size is finite. Okay, so let's go over this proof. And again, the proof intuition here is that the miner can help the friend. And you'll see that in the proof. So formally, the proof goes as follows. Let's prove by contradiction. Suppose indeed exists a non-trivial transaction fee mechanism that is both UIC and 1 SCP, and it works for finite block size. Okay. So because the mechanism is non-trivial, we know there must exist some bit vector B1 to Bn. And under this configuration, some bit must be confirmed. So let's call that bit Bj. So now imagine an alternate world. Suppose the world actually consists of B1 to Bn, and not only so, it contains many bits, and they're all bidding Bj plus epsilon. So imagine Bj plus epsilon is these users' true values. And the point is that there are many, many such users, such that the block space cannot accommodate all of them. So if you were to run the honest mechanism, then there has to be some unlucky guy, U, and he will be left out. He cannot be included in the block. Okay. So what happens is, imagine U is actually the miner's friend. So now, as I said, the miner is going to help you, right? How does it help you? It tells its friend U, instead of bidding your true value Bj plus epsilon, why don't you bid Bj instead? And once you do so, I'm going to pretend that the world actually consists of B1 to Bn, and I'm going to replace the jth position with your bid. So you are now Bj. And we know that when the world is actually B1 to Bn, Bj will be confirmed. And when it's confirmed, the payment has to be less than the bid, right? It has to be less than Bj. So now user U is guaranteed to be confirmed, and it's paying a price that's less than its true value, so it has positive gain. And the miner itself is just like indifferent, right? We have to use the key lemma. The key lemma says miner revenue is always 0. So miner doesn't care like what is included and confirmed, because it's always making 0 revenue. So this strategy allows the coalition to gain as a whole. So we can see it violates 1 SCP, and therefore we rule it out. Okay, so that's the proof. And so I didn't mention it explicitly, but this proof actually only works when the mechanism is deterministic. But actually, the theorem also holds when the mechanism is randomized too. So in our paper, we have the full proof for the randomized case. I'm not going to get into the details here. If you are interested, you can see the paper for details. So now let's move on to the second part of the talk, which is like crypto meets decentralized mechanism design. So given this impossibility, of course, the first question you want to ask is, what do we do now, right? And we want to somehow overcome the impossibility, and that's why we want to use crypto. So what, the one question is, okay, what kind of cryptography can help us? And I'm going to take a slightly different approach as Drake. Like, I'm actually not going to focus on how to make the crypto efficient and practical, because this is like the very beginning of our understanding. I want to first understand feasibility. And to start with, let's assume, we can use any crypto we want. And let's just assume the most powerful form of crypto. Because if, let's say, even with crypto, there's impossibility, like you don't have to worry about how to optimize it. But if with crypto we have feasibility, then perhaps then you can think about how to make it practical. Okay, so let's imagine we have general multi-party computation to our help. And in this scenario, we have some miners. The miners will be running a multi-party computation protocol to, and inside the MPC, you will be computing the rules of the transaction fee mechanism. So the users, instead of just posting their bits over a broadcast channel, now they will secret share their bits to the miners, and they can also prove that the secret sharing is correct. So basically, once the miners obtains the secret shares of the bits, they then run the MPC protocol to decide the outcome. Okay, so that's the model. And as I said, I'm not going to be particularly concerned about the details, how to implement the MPC protocol, and that's why we can just think of it as an ideal functionality, like a trusted third party. And this trusted third party is always going to honestly enforce the rules of the mechanism. Okay, so now we ask, in this model, is it possible to have a dream transaction fee mechanism? So first, I want to explain, before I talk about the findings, what's the intuition that this model can help? One intuition is exactly what I said. I said, earlier we had this impossibility, and among other difficulties, one challenge is the miner can help the friend, meaning the miner can arbitrarily decide which bits to include. It doesn't have to honestly execute the inclusion rule. But now this problem is gone, because this inclusion rule is actually decided by the MPC, and the MPC, we can imagine it's a trusted ideal functionality, right? So now the inclusion rule is always executed honestly. So it avoids this problem. And then there is actually a second benefit. I'm not going to talk about this very much in the talk, but I still want to just quickly mention it. So a second observation is, in the MPC model, the bits are sent in secret share format to the miners. So meaning, if I'm a user, I cannot see what other people are bidding anymore. And what does this bring us? It's in the plain model, in today's model, without cryptography, I can see other people's bids before deciding what to bid myself. And here, we want to use ex post notions of equilibrium, meaning even after I look at other people's bids, I don't want to change my mind. Bidding truthfully is still my best strategy. But when we have MPC, actually even this Bayesian notion of equilibrium may be appropriate, meaning I may not actually know exactly what other people are bidding. I may have some belief or a priori distribution on other people's bids, and my goal is to maximize my expected gain. Okay, so if you are not familiar with Bayesian equilibrium, it doesn't matter, because for this talk, I'm not going to be focusing on this point. I just want to bring it up. This is another reason why we can hope to overcome the impossibility. Okay. So I'm going to tell you our findings. Let me first give you the high-level picture. So we show that cryptography can indeed help us overcome some of these impossibilities. And maybe this is not surprising to you. But I also want to emphasize that if you think crypto, crypto often can do magical things. So if you think crypto can somehow magically just solve all the problems and trivialize mechanism design, then you are wrong. Because crypto actually doesn't trivialize the problem. Like in particular, it doesn't reduce this decentralized mechanism design problem to a classical mechanism design problem. And what's the reason here is because in this decentralized environment, there are still things that we care about that we didn't care about in the classical setting. Like the miner can still collude with the users, the strategic player or coalition can still inject fake bids. Some strategic users may even drop out to help their friends. So these are not things that we cared about in the classical setting. So even with crypto, this magical tool, this decentralized mechanism design problem is still technically fascinating. Okay, so more concretely, what are the results? So our paper also has like a lot of other results, like for infinite block size. But for this talk, let me just focus on finite block size. Okay. So we know in our previous paper, we showed that in the plain model without cryptography, we have an impossibility result. And the impossibility result holds even for one SCP. Okay, so we show that if we are willing to use MPC, then we can overcome this lower bound. But with a caveat, you can achieve UIC, MIC, and SCP, but you can only achieve one SCP. In fact, we can show even two SCP is impossible. So this is also partly why I said crypto doesn't just like magically trivialize the problem. Like it's still, the space is still kind of subtle to understand. Okay. So given that 2 SCP is not possible even with MPC, like you might want to ask, what if I do care about CSCP? I mean, 2 SCP or CSCP for, more colluding users. Because in practice, the miner can perhaps collude with more than one user, right? So if you want it, we can consider a further relaxation, essentially approximate incentive compatibility. So here, like in strict incentive compatibility, we want to say, my best strategy is to behave honestly. Deviating doesn't bring me any benefit at all. Whereas in epsilon IC, we say, okay, if I deviate, I can only gain epsilon more. And epsilon is so tiny that perhaps I just don't care about it. So this is the relaxation we are making. And interestingly, we show that even in this approximate IC setting, there is also an interesting separation between the plain model and the MPC model. So in particular, we show that in the plain model, yes, epsilon IC can help you, but it's not going to help you in an interesting way because like here, in the plain model, it's impossible. You can also think of this impossibility result as saying any mechanism that's incentive compatible must be degenerate. But here, it's like saying, okay, the only thing you can do is play trick with this, this wiggle room epsilon. So any mechanism you can possibly have is like epsilon degenerate. I mean, this is imprecise. You can think of this result as saying this. And more specifically, we show that the social welfare cannot scale. So in particular, scalability means the following. So imagine we take everyone's bit and we multiply the bits by 2, scale up by a factor of 2. If the mechanism is interesting, you should expect the social welfare to scale up accordingly. But we show this is impossible in the plain setting. And with MPC, we can overcome this impossibility. And in fact, we can even achieve optimal social welfare under certain scenarios. So this actually does give interesting mechanisms. Okay, so now I want to quickly talk about this mechanism and this mechanism because I think these are they have simple intuitions. The lower bound proof is actually the technically more sophisticated part of the paper, but I don't have time to talk about the lower bound proof. So let's first see how MPC can help us circumvent this lower bound under strict IC. And this actually, I already told you at the beginning of the talk, because it's the same mechanism. So posted price with random selection. So we do posted price. Anyone who bids at least the posted price is eligible. If there are too many eligible people, we pick a random K subset. And we said earlier in the plain model, this mechanism is no good. It's not one SCP. But here, it actually satisfies UIC, MIC, and one SCP. And the key intuition here, I'm not going to go through the proof, but the key intuition here, again, is because the inclusion rule has to be enforced honestly in the MPC model, whereas in the plain model, as we said, the minor can help the friend. Okay, so that's easy. But this mechanism is not 2 SCP, as I already told you, and because we actually have a lower bound that 2 SCP is not possible. So why is this mechanism in particular not 2 SCP? Because understanding this can help us understand how to get 2 or more SCP on the approximate IC. Okay, so why is it not 2 SCP? In fact, it's also very simple. So here's the problem. Imagine the minor colludes with 2 people, colludes with Tim and Fortini. And the posted price is 5. And Fortini's true value is 5. So Fortini is completely indifferent. Because if she gets confirmed, she pays 5, which is the same as her true value. So she always gets utility 0, regardless, right? But Tim does care because Tim's utility is much higher. So Tim wants to get confirmed. And because Fortini is indifferent, Fortini can just say, okay, Tim, I'm going to help you. I'm just going to drop out and not bid completely. And this can help you increase your chance of getting in, right? So in this way, this coalition can gain positively. So this is not an impossibility proof, but it does convey some intuition why 2 SCP is harder. And so if we want to get 2 or more SCP, let's say we are willing to assume approximate IC, essentially you also have to just fix this problem. And the intuition is like, as long as the pool of eligible bids is large enough, then if Fortini drops out, it indeed helps Tim, but it's not going to help him too much because his chance of getting confirmed does increase, but the increase is pretty tiny. And we can hope to absorb that with the epsilon. So that's what we are going to do. Essentially, we run the same mechanism with just one tweak. Essentially, if the pool of eligible bids, it's called candidates on the slide, if the number of eligible bids is too small, we will dilute the pool and pad it with filler bids, so this pool is big enough. And then we randomly select K subset from this pool, and if a filler bid is selected, it just occupies a space in the block and does nothing. But if a real bid is selected, then it'll pay R, and the minor still gets nothing. Okay. So we can show that this mechanism satisfies UIC, MIC, and epsilon C SCP for arbitrary choice of C. But the length of the padded pool is actually a function of the epsilon and the C. Okay, so I'm not going to show the proof, but this is the idea. And maybe in hindsight, it's a simple idea, but I think what's most interesting here is like this mechanism sometimes can achieve optimal social revenue. Because imagine the maximum possible bid is M. So imagine there are many people bidding the maximum possible bid. And I set the reserve price to be M over 2. So I is the posted price. So in this case, the block will be completely filled, right? And everyone who's confirmed has utility M over 2. So you are getting on the order of K times M social welfare, which is asymptotically optimal because K times M is also the best you can hope for. Okay. And what's interesting about this is because it shows the separation in the epsilon IC setting between MPC model and plain model. But I'm not going to prove this lower bound. You can read the paper if you want to see how this impossibility can be proven. And there are lots of other results in our paper which I didn't have time to talk about. Like we have characterization of infinite block size under the MPC model, detailed proofs, and we also have other ideas for overcoming these impossibilities. So just to summarize, I think this decentralized mechanism design space is quite fascinating because the classical mechanisms fail. And the work we are doing is kind of just the beginning. There are lots of things that we don't understand than what we currently do. Here are some of these open questions. Like for instance, our work showed, let's say, MPC does help circumvent some of these impossibilities. So can we make make it practical. Like, can we somehow use efficient primitives like commitments or customized MPC protocols rather than generic MPC? Can we think about other notions of relaxed incentive compatibility that overcome these lower bounds? How can we model the long-scale strategies? And this is also unknown. And there are many exciting questions at the intersection of cryptography and mechanism design. Okay, so this is all I want to say, but I also want to quickly advertise our other work called Rapidash. This is a different decentralized mechanism design problem. Like, you may have heard about fair exchange, like HTLC contracts. And there's a lot of discussions on like bribery contracts and how miner and users can collude to hurt the other user. So our paper is trying to design mechanisms that secure against miner-user collusion. And what's most cool about the work is the name Rapidash. Rapidash is a Pokemon, and its special power is that it can protect, it has fire power, so it can protect its rider from being burnt. So our contract is incentive compatible, and it incentivizes the player to behave honestly, and when they behave honestly, their collateral will not be burnt. So that's why we call it Rapidash. Thank you very much.